This is chapter 10 onto radical reactions. 10.1 is introduction to radical reactions. So, point 22 is describe the bond dissociation energy trends. Now, when we look at a tertiary CH bond compared to, let's say, a primary CH bond, the bond dissociation energy is lower for tertiary than for primary, and therefore the tertiary is considered the lower bond dissociation energy, or else it's also the weakest CH bond. So it will form the more stable radical. It follows the carbocation trend, like carbocation, because carbocations also have more stability with their tertiary. Likewise, it goes the same for radicals. Now to do practice 10.2 practice. If we had something like this, then we could draw resonance. This moves here, this moves here, this moves here. This may look like this. And note, this is very stable because it is a allylic radical. How do we know it's allylic? It's because we have a double bond and it's next to it. We have a double bond and it's right next to it. That's why we know it's very stable. There we have it in part 10.2. Common patterns in radical mechanisms. Point 23. What is the definition of propagation of radical mechanisms? What is the definition of propagation? Now, propagation for radical mechanisms describe the transfer of unpaired electrons from one place to another. We will explore that later. Now, 10.3. We will explore this in the upcoming following, but let's go on to 10.3. And 10.3 is the chlorination of methane. Now, what does radical chlorination look like? For methane. Okay, if we want to know the mechanism of radical chlorination, looks like this. If we look at point 24, let's say we have methane is CH4. We can use Cl2, which is a halogen, and we could use light. And this is light requires light. That's our radicals reactions require light or heat. And what do you want there? The halogenation. So radical reactions require heat or light. This is light. Radical halogenation requires heat or light. Basically, what do we get if we had something like this, let's say that was the carbon, then we will have a Cl like that, and we will have HCl, hydrochloride, hydrochloric acid, hydrochloric acid. Now what does radical chlorination look like? The mechanism of radical chlorination. Mechanism of radical chlorination. We start off with initiation. And initiation is basically we have Cl bond, right? We will start off with initiation, and we will use light to basically break the two bonds apart, like the following. We will do that. Basically what will happen is we will get Cl radicals. Initiation begins with cleavage. Initiation of radical chlorination begins with cleavage, otherwise known as initiation. 2 is propagation. Propagation is basically, what is propagation? Now, to describe this, for example, if this was our problem, basically what we would do is, basically if this was our problem we were describing and we were to draw the mechanism, we got initiation. Propagation would be this here, let's say CH4. We're going to do abstraction. Abstraction basically means now that we have one of these chlorine radicals, we're going to abstract this hydrogen. Abstract, you could see it basically just means snatching away the hydrogen from our starting reactant. And what will it do? This will generate radicals, right? Another form of radical. So this here is basically like coupling. That will be termination, but then we'll form another radical. When a radical moves from one molecule to another, or radical formation moves from one radical to another, that is called propagation, because you're propagating through to another molecule. Following, after this, let's say we'll have HCl, but that's really for later. Not really sure if this would be termination or propagation, but on the key it says it's part of propagation. Now, what is another propagation? Well, another propagation is that we could do the reverse. So now that we have this product, and if we were to abstract from the chlorine like this, this would be considered abstracting chlorine. So then we get something like that. We abstract chlorine to bond with the radical methyl. So termination is also coined as coupling. Now what does coupling look like? Coupling is you look at every single radicals you possibly could have formed from propagation and initiation steps, and just combine. So you remove that radical and it becomes a bond. Two radicals combined could become a bond. Bonds are more stable. That could be coupling, and it would be Cl. Well, we also initially formed the methyl radical, and that looks like this. If we combine this and chlorine, then we can get this is not chlorine, this is carbon radical. Then we can get this formation. These are both known as coupling. And if we were to, another possibility is using this methyl radical, we could couple these up and we get this new molecule, and this is just ethane. We get ethane if we couple those up. Was 0.24. 0.25 is 10.4. Thermodynamics. Dynamics. 25. So, how do we explain thermodynamics? How do we use thermodynamics to explain radical fluorination, iodination, and bromination, and chlorination? How do we compare the following? Well, we could just observe. We can observe the bond dissociation energy of relevant bonds, and iodination is the only product that is positive and not exothermic. This one is no, it says, the answer says it's the only one with positive and not exothermic. It's the only one that's positive and not exothermic. Now, let's look at the more following. If we look at 10.5, selectivity of halogenation. Why is bromine more selective than chlorination? Why is bromine more selective chlorination? Now this one I still don't know why. Why is bromination more selective than chlorination? The reason why is bromine looks, this is what bromine looks like, and this is what chlorine looks like, but and also bromine has higher differences in transition state energy, activation energy, whereas chlorination, they're pretty much the same. Transition state, chlorine, and that's why bromine is more selective, because it's endothermic, but also what? It retains more radical character. Because it's closer to products, I think. Right. Actually, it should look something like this. There's an intermediate. Intermediate is closer to transition state, whereas for chlorination, not very so. Still confused a little bit on this one. Now, if we were to say there was this molecule, we reacted with X2 and light halogenation, we will form this and this. Which one is more major? It depends on bromine or chlorine. Now, bromine, there will be selectivity for this, I think, but not too sure. If we had this molecule and we brominate with like radical bromination, outcomes could look certainly like this. We can have bromine here. You could have bromine here, and we could have bromine here. There. 10.6 is stereoselectivity. Now if we look at point number 27, how is stereoselectivity affected by all of this? Note that after radical halogenation does not care for selective stereochemistry. So let's say, look at this example. This is a chiral center, but then this is a racemic because it doesn't have any stereoselectivity. You break bonds like we saw in the mechanism, initiation, propagation, termination, and it'll form new bonds and it will have no selectivity. 10.7 is allylic bromination, which is important, and this is point 28. Now the question asks, what must be used for allylic bromination, and describe its mechanism. Now allylic bromination requires a special component known as NBS. Now NBS looks like this. This is what NBS looks like. It's got a bromine attached to a pentane looking containing nitrogen, but it has two carbonyls like this. It has like two ketones. It's got a nitrogen inside a pentane shape, and it's got a bromine. Now, if we look at this, is known as N-bromosuccinimide. N-bromosuccinimide. Now, if we were to look at this, allylic bromination requires using NBS and light for selectivity. Now, if we look at this compound, react with NBS and light, what will happen? We know we could get allylic beings next to a double bond, so we could get this formation. Wait, this is the intermediate, so the radical can end up there. We'll get to the mechanism later, but why is that? Well, if we look, it's because there used to be a hydrogen here. Bromine basically abstracts the hydrogen. That's why we get the electron ending up single there. But if we do resonance, this can combine here, here, and that out of there. So then radical can end up like this. If that is the case, there are two products. That means we could get this, and we can also get this. These are the two products for radical bromination. Now, let's look at the possibilities with this. How can this radical bromination, if we abstract the hydrogen there, basically what can happen is we will get, now these are separate, we will get this, and if we combine we will also get, sorry, did not mean to draw another line, that will be there and this will be here. So these are the intermediates. If we draw the products, it will look like this. Bromination looks like this. That's what bromination may look like. Oh, sorry. This is allylic bromination. Bromination and allylic bromination are vastly different. Okay, that was point 28. Point 29 asks, what are the reagents for anti-Markovnikov addition of HBr? HBr and Markovnikov, so that means H2O2. So let's see if that's correct. We need peroxide and we need the hydrohalogen. And this will result in anti-Markovnikov radical addition. Note that this is a radical addition. Note that only HBr is possible for anti-Markovnikov radical addition. Only HBr, not HCl, but HBr. And it'll form racemic mixtures with equal proportions. 30, point number 30 is 10.11 radical polymerization. Radical polymerization. Now, what's the mechanism? Radical polymerization. Now, before we do that, we need to finish with the mechanism for radical addition, anti-Markovnikov addition, hydrohalogenation. Radical addition of HBr to alkene. Now, what does that look like? Okay, so radical reactions always have initiation steps. We're gonna start off with peroxide, and we're gonna break apart like that. How? Because that's homolytic cleavage, and we need heat or light. That looks like this. And so now we need turns out abstraction can also happen in initiation. Let's say we had OH and HBr. Abstraction would look like this. And abstraction will look like that. This is called hydrogen abstraction. Hydrogen abstraction looks like this. What we get is H2O and Br radical. Now, what does this mean? It means we can use this Br radical for our propagation. Now, what would propagation look like? Hold up before we get to all of this. So we were talking about anti-Markovnikov radical addition the whole time, but we didn't discuss the basic big. We didn't draw the basic picture. If you had HBr and H2O2, what would the product look like? Antimarkovnikov, so then Br will end up on the less, excuse me, substituted, and H on the less substituted. That's one. So back to our mechanism. So if we want the Br to end up on less substituted, we will move on to propagation. That's the jumping of electrons. So if we had a Br with an extra unpaired lone pair, this is reactive. What would it like to react with? Well, let's say this, okay, so it's not that molecule, it's something else. Let's say this was a molecule, a starting molecule. It will jump like this, and this alkene will jump like that. And that's only half of it, and where will the other radical go? The other radical will go on the more substituted. It looks like that's why we shall get a radical that's more substituted over there where the Br ends up on a less substituted. If that is the case, then this is our radical, new radical, and what do we do from there? Are there more propagation and abstracts? It's a possible abstraction possible. Yes, it turns out abstraction can also happen in the case with this molecule. Let's redraw that here. If we have an abstraction molecule like this, and we have, let's say, HBr. If you have HBr, that came from here. It looks like we could still use that. Then we can abstract the hydrogen off the HBr, and basically we get bromine radical. And it looks like we also get the hydrogen there. Well, why is this important? Because propagation, we learned that we start off with consuming the bromine radical, but we also form again in the end. This means this is like a catalyst, or what do you call it? It gets consumed but produced again, so it kind of cancels out. It's like those spectator ions we learned in general chemistry, except it's not. So we learned of abstraction, and now let's go to termination. Termination is basically we have the two bromine radicals we were talking about. And it could form the bromine, you form the dibromine, Br2. That is through the process called coupling. Coupling to form the bromine. Let's do some practice. Let's say we had a molecule that looks like this. We reacted with H2O2 and HBr. What will basically happen? We learned earlier that under such conditions we can form anti-Markovnikov. If it's anti-Markovnikov, then we should get something like this. Is that correct? Let's check. Turns out this was not completely correct because we had to account for stereo isomers. What does stereo isomers mean? We basically mean that, okay, we're starting from the start. If we were to draw something like this, basically no, it will go anti-Markovnikov, that's correct, but also this here is a stereo center, so we could form something like this, or we could form something like this, because it's a racemic. These will be in 50-50 proportions. Okay, let's look at another example. For example, if we were to look at this compound, if we were to look at this compound, HBr, let's say for this HBr, H2O2, basically then we should get anti-Markovnikov, and that means if we have something like this, we'll get Br. This is not a racemic, so this will be our only product because these are two hydrogens. They're the same thing. That was part C. Am I correct? Okay, turns out that was not correct either. So we do get anti-Markovnikov. However, this is not the only product because we're dealing with the double bond here. This can be a stereocenter. So we'll get racemic here. We'll get coming out like this, or we will get something like that. These will also be a 1-to-1 ratio. Now, if we look at this molecule, I think we should get the pattern by now. React with HBr, H2O2. The answer to this is also Br like that, but this looks like a stereocenter. Is it not? Let's check. This is racemic. This looks racemic to me. Apparently it's not. This is not racemic because this side and this side it's symmetrical, so they're the same. We view that the same. This is a chiral center. We learned this is a chiral center. No, sorry, this is not a chiral center. That's why we only get this product. Now, if we look at this molecule, and do HBr and peroxide, H2O and peroxide, what happens? We will get also Br like this. Now, this is a stereocenter. This is a racemic. It's not. Let's see. Looks like yes. The B can come out front, or it could go out like this. Br. So this is correct. Now, let's go on to 10.11. 10.11, it goes on to touch radical polymerization. That's point 30. What is radical polymerization? What's its mechanism? Mechanism for radical polymerization. Now, if we were to start off with something like hydrogen peroxide as our initiation, we can use heat to cleave this and get something like this. But also, we know that if we have an alkane, this can undergo sort of like a reaction with hydroxyl and heat up like that. We will also get OH get a radical like that. Now basically, what are we doing? If we have a molecule that looks like this, we can do basically what we solve. Now we are on propagation. If we have something like that, this will go like this. So we'll have RO. We'll have something that looks like this. Note that we formed another bond. And so if we also go another propagation, we'll form another bond, or another carbon I should say, and then it shall look like this. And then so on and so on. We could repeat what we see here and here. This is called polymerization. Now how was this possible? Well, we started off with this molecule by starting with an alkene and a peroxide OH hydroxide that broke off into a radical. So what we learned is we could start off with a radical hydroxyl ion radical and react it with an alkene and keep on building and building and building until we get a long change of our desire. But at some point we should end this because we don't want a polymer that endlessly keeps forming and forming. Well, it should be pretty easy if this was our R that we made. We still have yet to react. Well, we could just couple it up. OH OR. So we could just couple it up, and basically what we get now is we can now get this OR. Or we could also do something like if we have this and this, these two can form a new bond and form 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be our termination product. So that was point 30 and 31 is halogenation as a synthetic technique. It's not point 21, but I'll just show it. Let's say we had this in Br2 and light. We learned that Br2 can will go through abstract hydrogen, and Br will instead go on the most substituted because it's just like the carbocation trend. And what can we do from there? We learned about elimination, right? We can use elimination using like N sodium and amide, sodium amide, NaNH2 to basically do something like form something like this. Elimination. Not too sure if this is the right one. Let me just check. Yes, sodium amide is a strong base, and that's how we can get this product. But also we can get something like, what can we get? We could do substitution using something like so and so. Substitution to do something like, sorry, we could go through substitution to form something like that. This brings us up onto the next chapter, which is on synthesis. As a last side note, we will see what we can do here. Let's say we want to do this. What are the steps we can use now? If you want to do elimination, there's got to be a halide, because that's what we learned so far. So we could do bromine, molecular bromine and light or heat. This will abstract the hydrogen onto most substituted Br. Now illumination, we learned there could be Zaitsev or there could be Hofmann. It looks like we're using Hofmann. Now how do we approach Hofmann technique? Hofmann technique is favored when we use a strong bulky base. This is a Hofmann. So if you want to use something bulky, we could use tert butoxide, or we could use something like this we saw earlier. Yeah, this will result in 92% of this product, and the other minority will be the Zaitsev, which would obviously point this way, but that's not what it's asking. So let's go check 10.23. 10.23. Sorry, it's 10.21. Why is it 10.23? It's 10.21. David Klein. Sorry, no, it is 10.23. Conceptual check of 10.23. The answer key is not showing the correct textbook version, but looks like it might be it. Wait a second. Yes. So again, we could use strong, large, bulky base to get Hofmann product, which is following as shown below. Now, that was chapter 10, halogenation. On to the next.